Good evening, everyone. My name is Nidin Vinayakan. I'm from India. I'm mainly working on web technologies. Right now, you can find me in Twitter. Maybe some of you know me, like this thumbnail. I'm on Twitter on 01 Alchemist. Right now, I'm working on a startup company called InstaMotion, powered by Alliance. So we are actually trying to sell cars online. So you can buy cars online with a mouse click. If you don't like it, you can return it. Yeah. So you all know we have web workers, and it's enabled multi-threading at some extent. So for example, if you have a memory in worker 1 and you have a memory in worker 2, if you want to share this data, we can copy like one by one, one bit by one, using post. That's not the efficient way. Another thing, you can actually post this entire memory to the worker 2, then it will clone. It's actually copy the memory 1, the entire memory block, and create a new memory. So in the memory, it will take like 2 blocks of memory. Another thing, you can actually transfer this entire memory. The problem is it's fast, because there is no cloning, just transfer the memory. The problem is it's detached from the CPU 1 and no more access. And if you have an object, it's even crazy. It will deserialize and deserialize during this clone, and it's very expensive. So for a real-time shared memory parallel programming, this is not an option. Yeah, there's good news. We have now ECMAScript 2017 or ES18, and there's a new feature, shared memory and atomics by this Lars T. Hansen. So we have a new API or an object, SharedArrayBuffer. You might hear the array buffer. So when you create an array buffer, it will allocate a memory block in the RAM, and you can work with it. But the problem is you cannot share it. With SharedArrayBuffer, it's the same, but the underlying memory is shared between all the workers. So the API is similar, but the difference is you don't need to transfer this shared array buffer because it's already shared between workers. So just post it. So it will transfer the reference to this memory to all the workers, and all the workers can access the same memory. It can read and write to this memory. So something like this. We have worker, CPU 1 and 2, and a memory shared between 2 workers. So let's do some execution. So we are actually counting like 200 million numbers. So how long does this program take? Time for 200 million iterations. How can we make it faster? Run iterations parallel. So it's just a hypothesis. How much faster we can run parallel in 2 CPUs? If you have 2 CPU, yeah. We expecting speed above 2. Maybe a little less, because considering forking of workers and message passing, maybe a little less than 2. But actually, it's slower. Why? Because we forgot these little guys. Because each CPU has its L1 cache, and also on top of it, there's L2 cache. So if you want to access the memory, it will copy to L2 cache, then L1 cache. So if you are doing a computation only in one thread, it is faster because all the memories are immediately available in L1 cache. So the accessing is very fast. But if you want to share that operation between different workers, you need to go through these things. And also, there's another set of problems, because it can cause data arrays. For example, the initial value we are counting. So the initial value is 0, so it will copy to L1 cache, then it's available to CPU 1. Maybe CPU 2 is already fetched this data, and it's increment by 1, and it's write to the shared memory. But CPU 1 doesn't know it. Okay. Then what will CPU 1 do? It will also increment by 1 and write into the memory. But we will actually do 2 additions, but at the end, we will get only 1. But we should get 2, because there is no coordination between CPU 1 and CPU 2. So for that, we need new set of APIs. It's called Atomics. So we can actually lock one particular lane of memory access. And during the lock, CPU2 cannot read or write from that memory location. So using atomic operation, we lock the memory, and we load it, and we add it, and store it to this memory, and release the lock. Then CPU2 can increment or read and write to this memory using lock or without lock. If it's not locking, the same problem might happen. And this is a new API, Atomics. It's only available in integers, so we cannot do float atomics. So you can only use for integer arrays. So when you do like this atomic add in 3201, so at the end, you will actually get the expected result. So let's do small demo. Oh, sorry. So. Okay, this is our simple program counting. So let's count in single thread. So it takes around 400 milliseconds to count these 200 million numbers. Then count in parallel. Yeah, it's take longer. Not only that, the count is actually rubbish data. It's not even 200 million. If you run it again, it's different. Each time you run, it's different data because there's a data race. It's not coordinated. It will write depending on the hardware, depending on the cycle, how CPU is busy. The CPU will schedule these instructions independently. We can run with Atomics. It's quite slow because it's actually doing it kind of serial, because it's locking the memory and adding it. So during that lock state, the CPU1 cannot add it. So yeah, we will get the exact expected result, but it takes like 13 seconds. That's ridiculous. It's parallel, but it's actually way, way slower than single thread. That problem is, I will show the code. One sec. Yeah, it's actually iterating in a for loop. It's actually accessing this atomics add every time, like 200 million times using atomics add, which is very slow because it's locking 200 million times. That's very, very slow. So I have another variant, count parallel with atomics, but with optimization, like symbol optimization. But this is very fast. You also get the expected result. Then when you run the single thread again, so when you run a single thread again, it's actually much faster now because it's actually V8 is optimizing it. It's 50% faster now when you compare it with these 400. So in the optimized version, what I'm doing is, because accessing memory is expensive, so when you distribute some data, so I'm actually using a local count, then I'm actually counting locally because I have 8 threads, and I distribute this 200 million counting to the 8 threads. So 200 million divided by 8. So in this loop, it only uses the registers. Like this let count is a local variable, so it will store into the CPU register. And when doing this for loop, the accessing this count and incrementing, it's in the register, so it's very fast. Then after counting that local numbers, only using one atomic add. That's why it's faster. So if you're really doing any real parallel programming, the atomics is very good, but you should not do it if you don't use it, or if you don't really need to synchronize the data. Let's go back. Yeah. Then, yeah, a little demo. So I was working on a Three.js render engine. It's actually a ray tracing engine. So maybe some of you know ray tracing. So Three.js is actually, by default, it's using WebGL. So using WebGL, it's very hard to mimic how the physics of light. And it's very hard to mimic this global illumination and realistic shadows and soft shadows. So I developed a CPU version of ray tracing engine using shared memory. And let's, OK. So this is a Three.js scene. And it's a standard testing model. It's a Stanford Dragon. And in order to improve the ray tracing performance, I need to build an acceleration structure. For this, I'm using KD tree, so I need to build the KD tree. It's also building parallel, so it took 2.8 milliseconds. Then I can start ray tracing. OK. So it's actually ray tracing in real time in JavaScript. So it's actually splitting the scene into, or image into 8 tiles, and it's ray tracing 8 tiles at a time. So for a JavaScript, yeah, this ray tracing is quite fast in this case. I can actually turn around. And sorry. Yeah. When you toggle the WebGL version and the ray tracing version, you can see the shadows are very nice. And also there are color bleeding here, the red one, and also green colors here, which is very hard to mimic using WebGL, because WebGL is a rasterizing API. It's not a 3D API. Everyone thinks it's a 3D, but it's actually flattening all the 3D data into 2D. In this ray tracing, we have a real 3D scene, and I'm shooting rays into the scene and intersecting to this 3D model. And depending on the normal, it will reflect, and it will try to find out the accurate color. So if I let it running a little longer, you will get like a realistic image. Let's put it down. So there's another Three.js demo. It's a Three.js demo scene. Those who are using Three.js, in the example, it's actually object data with materials and textures. So this is actually vanilla JavaScript. And it was really tough developing something like this, because I have only shared memory, and it's linear memory. Like, there is no structure, or I cannot copy objects. So I need to put everything into shared memory. It's very linear, so I need to write objects into this memory. So doing manually is like, it's not scalable, and it's not reliable. If there's a bug, it's very hard to detect. So let's. The problem is like this. So I have an object, and object has some properties. And if I cannot write or read directly to this shared memory, because it's a JavaScript object. What I need to do is, I need to serialize, like kind of encode this object into like normal binaries, like object ID and property 1, what's the value. So I'll write directly into this memory. It's very not optimal, because for a bigger project, it's not an option. So I need something like, OK, I have an object. I'm using TypeScript now, so I have an object, so I need to do this automatically. So I am searching for in internet, what's the solution? I didn't find any good solution. So I created a compiler. It's called TurboCompiler. And it will take TypeScript object, like class, and it will automatically do this thing. When we create a class inside TurboScript, it will actually allocate my memory inside shared memory, and it will return a pointer. So I can work with that pointer. So yeah. So TurboScript look like this. So for example, it's a vector, and vector has x, y, z. So for you, it looks like normal TypeScript. The only difference is you need to delete this allocate memory manually, like C++. So I can create this object. So here I am creating this new vector, and I am exporting this function. When you export a function, it will actually export. It will create a module and export this specific function to the JavaScript world. And from the JavaScript, you can access this new vector. So it will create new vector and return a pointer. And later, you create two vectors and use this function to add it. It will add and return a new vector. Then if you're done with that vector, destroy this vector. Otherwise, it will leak the memory, and you will die. OK. So currently, TurboScript is like this. It's a subset of TypeScript, but it's little more. TurboScript has operator overload and memory pointers. That's the two difference for now. And it can compile to normal JavaScript, asm.js, and WebAssembly. In WebAssembly, it's not really usable because WebAssembly don't have shared memory. So when WebAssembly 2 release, I can really test how the performance. I can compile the same code to three different targets: normal, vanilla, JavaScript, and asm.js and WebAssembly. So it will be a really nice tool to compare how these three things performing. And it's still work in progress. So I can actually, I'm trying to implement it. So compile complete TypeScript to like JavaScript, WebAssembly combination. So if some feature is not supporting in WebAssembly or in my implementation, because in order to support all the JavaScript features, I need to re-implement all the JavaScript virtual machine inside WebAssembly. That's not doable for now. So I can actually selectively compile some hot functions into WebAssembly and other functions into normal JavaScript and connect together. For example, DOM access things, I can actually compile to normal JavaScript, so it's easy. Maybe some hot functions, very number crunching and something like that, I can actually compile into WebAssembly or asm.js. Then you can utilize this WebAssembly, because normally when I talk with normal JavaScript developers, they are not interested in WebAssembly, because right now only C++ can compile to WebAssembly, and when we talk about WebAssembly, they don't know what is it. And they cannot really use it. You can still write a expression in text format, which is really not scalable, or it's very low. It's meant for debugging, and no one is writing in a real big project in it. So this is also a good tool for normal JavaScript developers, because the syntax is similar. And yeah, so benchmark. So when I'm using normal JavaScript, I need to, I mentioned I need to create a acceleration structure for ray tracing, which is KD tree. So to building it, it will take a little bit more time, because it's actually splitting the 3D scene into 3D space into different small pieces. Normally, I need, without TurboScript, I need to build once in the main thread and copy these objects through post message. Then actually it will clone, and the performance was low, and it will take more than 1 minute to just initialize this Stanford Dragon. Right now I am actually using TurboScript, and it will compile, and at the end it will just return a pointer to this KD tree. And I can just share that pointer to the workers, and the workers immediately has access to all the KD tree. So it can just start ray tracing. I will show you some syntax. Okay. So there's an array. Okay. One sec. Okay. There's an array example in TurboScript. So you can also export an entire class. So it will export something like this. So we will open a asm.js so it's easy to read. Okay. So it will declare functions like this, like data new and data set. So from the JavaScript, you can actually use data new, so it will create a new instance of that data class. And one problem is I'm working on it. I'm working on a wrapper for these turbo classes. So from the JavaScript, you can access like a instance dot properties. Right now, you cannot access properties, but you can access methods. So you can access a set method, or if you want to access a v1, so you need to like get v1. Float 32. So you need to do something like this to access the property, because when you instantiate the class, what you are getting is a pointer. So you cannot, because it's in 32 number, you cannot dot it because it's a pointer. So you need to do like this. But I'm planning like a wrapper function around the turbo object, so it can actually export automatically a JavaScript wrapper. Then you can use normal things. But I don't know how fast it is, because it will create an object. Maybe for a bigger objects, like if you have a very huge, for example, if you have a big scene of like millions of triangles, you can create a wrapper object for the main root objects, like a scene. So from the scene, you can actually access a lot of the properties. That will be useful. And yeah. And also, I am using this warped tool. Like I can compile WASM to this text format, so I can actually debug what's actually going with my WebAssembly. It's easy for debugging. Also, I have a log, so it will emit all the data, like what bytes are returning. So it's also easy for debugging, like everything in a log file, but it's formatted. Yeah. And yeah, any more questions right now? No? Okay. Yeah, that's it. It was actually quick.
Thank you so much, Nidin.
Thank you.
For the excellent talk. So we have a break scheduled now, 15 minutes, and then the last 2 talks of the conference. We also have our last community event if you want to go and check out another live JS performance.